I'd like to introduce to you the idea of linear stability analysis and take you through the theory just quickly and then do a couple examples and then show you some code. So let's start out with a dynamical system. A dynamical system is basically a system of differential equations. Dynamical because normally they evolve through time. So for an example, or sort of a canonical version, is just dx by dt is some function of x, and it could also be a function of t, but I'll just leave that out for now. So where x comes from Rn, so x could be some n-dimensional space, and f maps from Rn to Rn. So, and it has to, because basically we're talking about this dynamical system in n-dimensional space. So there are n dynamic variables, and f basically computes the derivative, or the rate of change of each of those n variables. I'll give you an example later on. Well, why don't I... No, I don't have an example right here. Okay. So let x star be an equilibrium, which means that f of x star equals 0. An equilibrium means that the rate of change of all the variables is 0. So now consider perturbations from that equilibrium. If you're at the equilibrium, you stay there. But let's perturb a bit away from that equilibrium. We'll call that perturbation A. A also is an element in this n-dimensional space, and I can draw it. So let's say here's our x. Let's say A is this sort of little deviation. So this is A. So this new thing is x. This x star plus A. So we're going to do a change of variables now, and A is going to be our new dynamic variable. So we're going to rewrite our system of differential equations in terms of how far we are from that equilibrium. So dA, I could rewrite that as A is x minus x star equilibrium by dt. But of course, this thing here, this x star, is just a constant. So this is really just the same as dx by dt. So now I have what I need to rewrite my differential equation. So I'm rewriting this thing up here now, but in terms of A. So dA by dt is f of x star plus A, right? This was x, and I just replaced it with the version that has the A in it. Okay. Now, we're interested in what happens in the neighborhood of the equilibrium. So we're going to sort of zoom in on that equilibrium and look at how things behave for these little deviations, these little perturbations. So to do that, we're going to use Taylor's theorem. So Taylor's theorem applied to F, centered on the equilibrium. So A is going to be our displacement. It's going to be our little delta that we're going to use in Taylor's theorem. So Taylor's approximation centered on the equilibrium is, well, it's just the function itself centered on the equilibrium plus the first derivative term evaluated at the equilibrium times our deviation or our perturbation from there, plus dot dot dot, but we're going to just remove and ignore higher order terms. So ignore higher order terms. So this is stuff that would involve quadratic and cubic functions of A. Getting rid of those, just linear. This is a linear approximation. Okay, now recall that x star is an equilibrium. So what an equilibrium means is that f of x star, f evaluated at the equilibrium, is 0. So we can actually ignore this first term. It's just 0. Whoops. So then we can rewrite it as just this second part here. the gradient or the Jacobian evaluated at the equilibrium times our matrices or displacement A. Sorry, times our variables or displacement A. Okay. So as I just said, that grad f thing, this thing here, is actually a Jacobian matrix. So the Jacobian is when you have a function with many inputs and many outputs, the Jacobian is basically a collection of the derivatives. So it's defined as, so if f is basically, has a whole bunch of inputs, x1 through xn, and each of those inputs contributes to a different output function. So I have n output functions in this case. And each one of those f's is a function of all those x's. So the Jacobian is basically putting them all together. So df1 by dx1, df1 by dx2. So these are partial derivatives. Df1 by dxn. And work our way down, dfn by dx1. And down here to finally dfn by dxn. That's the Jacobian matrix. So we can compute all those because we know what those f's will look like in our differential equation. System of differential equations, they'll just be functions. Okay. Notice that A is an equilibrium, A equals 0 is an equilibrium of this system. Right? If you set A equals 0, obviously the right-hand side will evaluate to 0, and so the derivatives will be 0, equilibrium. So what do those solutions look like around there? Well, consider the 1D like scalar differential equation, dy by dt equals lambda of y. So y and lambda are both scalars. So if lambda, so the solutions look like this. I mean, that's the formula. So what do those look like? Well, if lambda is greater than 0, these look like exponential growth. And I'm just sort of drawing a few examples here. This one, even underneath the axis, it'll grow in the negative direction. If lambda is less than 0, that's exponential decay. So that'll be like this, and this, and that. Right, decaying down towards 0. So in the one on the right-hand side, when lambda is less than 0, everything's converging to that equilibrium at 0. So this is the 1D analog of a higher dimensional phenomenon of solutions converging onto the origin. So if our system has more than one variable, then we get those lambdas. So this lambda is easy to see here. It was right in our differential equation. Where is that when we've got this whole system of differential equations where this thing is a matrix? Well, those lambdas come from the eigenvalues of the matrix. And so in this case, you just have to trust me on this. There's a lot of theory that goes behind this. I mean, it's not that deep really, but it is it's kind of a full lecture in and of itself, but we'll just sort of take it for granted then that the eigenvalues, in fact, it's actually the real part of those eigenvalues that give you the lambda. I guess it's worth saying up here. If this lambda is complex, you'd actually get oscillatory. In fact, the real part gives you the exponential growth or decay, and the imaginary part gives you the frequency of the oscillation. But that's a little more detail than we need to get into right here. For now, we'll just be happy with the real part. If the real part of all the eigenvalues are less than 0, then that equilibrium is stable. The origin is stable. Now remember, we had an equilibrium. We linearized our system of differential equations around that equilibrium. That's how we got our Jacobian matrix. Our Jacobian is specific to a particular equilibrium point. So you find the eigenvalues. If all the real parts are negative, that means that equilibrium is stable. If one or more of the eigenvalues has a positive real part, then it's unstable. So I don't say that explicitly here. Now, even though we linearized and we found out the linear stability of that equilibrium, you can show that that linear stability carries over, at least in a neighborhood of that equilibrium, for the nonlinear system. Because when that a is really small, the linear terms will be the most significant. Higher order terms, like small numbers raised to higher powers, are really small and negligible. So it's the linear terms that matter the most. So the linear stability carries over, at least in a neighborhood of that equilibrium. Okay, so here's the recipe for linear stability analysis. First thing you do is you find an equilibrium, because this is specific to an equilibrium. Find equilibrium, and we'll call it x star. So we compute the Jacobian around that equilibrium. Oops. Of f. That's what this thing is. And I'll just write like that because we are computing the Jacobian at the equilibrium point. Next, we compute the eigenvalues of the Jacobian. And then finally, you look at the real part. If at least one eigenvalue has a positive real part, then it's unstable. Unstable. That means there's one direction that things leave. On the other hand, if all eigenvalues have real part less than 0, then it's stable. In fact, we'd call it asymptotically stable, but that's a distinction we don't need to get into. The distinction is, what if one of the eigenvalues has exactly 0 real part? That's still stable, but it's stable in a different way. Things can sort of sit nearby but not converge back to the equilibrium. When all the real parts are negative, that actually they actively converge in on the equilibrium. That's asymptotically stable. Okay, let's use this recipe on an example. Here's the dynamical system. Two variables, x and y, and so therefore two differential equations. Now I've observed, and I won't prove it, but you can prove it for yourself, that there are two equilibrium solutions. There are more than two actually, but I'll just focus on these two. There are more than two because we have a periodic function here. But x equals 1 and y equals pi over 2 will set those differential equations to 0. So let's focus on that one first. So we have to compute our Jacobian. That means we have to take the derivatives of these functions here on the right. We have to take the derivative of each of them with respect to each of the dynamic variables. So I'll call this first one f1 and the second one f2. So the partial derivative of f1 with respect to x is, I'll write it in red, di by x1 of x1. I'm just writing it out so that you can see what I'm doing, right? It's this function up here. So the derivative of that with respect to x is, well, I'm going to have to do some, what is it, product rule? Derivative of the x times the rest, so 1 minus x times y minus xy. Yeah. And this other one, now the derivative of this same thing with respect to y. Well, it's just x times, x times 1 minus x. Okay, so moving along faster, the derivative of this next thing with respect to x is cos y. And the derivative of f2 with respect to y is negative x minus 1/2 sine of y. So these are my these are my terms, sort of the derivatives that will go in the Jacobian. But now I need to evaluate those at my equilibrium. So looking at the equilibrium 1 pi over 2, I've just plugged them in, x and y. So I've worked this out already. If you plug those into df by df1, whatever, you get that. So working all out, skipping the details, which are really simple, my Jacobian matrix looks like this. So it just happens to be diagonal. It doesn't have to be diagonal, but it's convenient that's diagonal because we can read the eigenvalues off. The eigenvalues are negative pi over 2 and negative 1/2. The real parts of those are both negative, so therefore that equilibrium is stable. I'll demonstrate that momentarily. What about the other, did I say that was it? Yeah, the other equilibrium, 1/2 0. Again, I worked out the Jacobian, evaluated the Jacobian matrix. And there it is. And I computed the eigenvalues by hand, but you can also just use Python. And I get positive negative 1/2. So one of them is positive. So therefore, it's an unstable equilibrium. Okay, let's see that working in real life. Okay, so I've got this. I've coded it here. So this is the function that evaluates the right hand side of the differential equation. So you can see that it matches there. So dE2. Let me. Here's just a loop that computes a whole bunch of random initial states near 1, comma pi over 2. So near the equilibrium, a bunch of random initial states. I'm going to solve it and then plot those trajectories. So you can see they all do sort of, well, they're all kind of coming into this point in here, which is at 1 and pi over 2, which is 1.57 something, right? So that actually is evidence that it's converging. I mean, that's evidence that it is an asymptotically stable equilibrium because they're converging to it. Contrast that to the other equilibrium, which we determined was unstable. So you can already see what the plot looks like, but I'll rerun it. So starting from all these sort of random positions around here, you see they start to come in, they kind of converge in this direction, sort of this diagonal along here. They do come in, like this one's coming in here, but then they all leave along this direction. So if you know, if you look into dynamical systems theory, this is the direction that's corresponding to the eigenvalue of negative 1/2. Yeah, negative 1/2. And this is the direction that corresponds to the eigenvalue of 1/2. And so things come in along the direction of the negative eigenvalue and then leave along the direction of the positive eigenvalue. And well, there's the how you get the eigenvalues to that. I don't have to show you the eigenvalues of the other one. They're pretty simple. Just another example here. Here's a different dynamical system. It's a decaying harmonic oscillator. So it's a linear differential equation. So the Jacobian, you don't have to really, it's easy to take the derivative because it's already linear. But so there's the dynamics equation, and I've set this one up so I can animate it. So it's going to run a bunch. So it's going to run a single one, and I can animate it over time. So we start out there, and then you can see it's spiraling in. So spirals in. Well, does that pan out from the Jacobian, the eigenvectors of the Jacobian, eigenvalues of the Jacobian? So if you were to take the Jacobian of this, you would get a matrix that looks like that. negative c, negative theta, theta, negative c. And if we get the eigenvalues, you can see there are they're a complex conjugate pair of eigenvalues, and the real part is negative 0.2 in each case. So that tells us that the equilibrium at 0, 0, which is what this is asymptotically stable.